So today we see nonlinearity and language models. Also on the part of like the demo which went terribly wrong. Now that I know why, I feel super stupid because it was obvious why it was not working, but it's okay. So today, first of all, nonlinearity. So we see that what we saw before, like the log linear model, generalizations to n labels, whatever, it doesn't always work. There are some problems we cannot solve. We're gonna see what we're gonna do about it, what we can do about it. Then we're gonna see the n-gram language models. So we discovered this very simple model that can predict the probability of a text. So we're actually going more towards language modeling. You probably were looking for workflow. This model just works by counting and dividing numbers, and it's very simple, also very limited. So to address that, you're going to see a neural language model. So we'll expand the n-gram model with actual parameters we can learn, and we can actually see that this will learn powerful word representation, which you may know or may not know with their most popular term, word embeddings. So exciting, hopefully. Let's start with nonlinearity. So far, we have these models, right? But they model linear functions. So you're now probably familiar with this f of x or f of x double b, which is basically this matrix vector multiplication or vector multiplication, which is x1 w1 plus x2 w2 plus some x yes, roughly, yes. So the problem is that you remember when we talk about inductive bias, we choose specific functions, which means that our model can only solve specific problems, right? So, for example, when we choose only the derivable function and functions that can be calculated at every point, we may be giving up some function that if we found a way to go around the fact that there are some holes, they could solve other problems. Something similar is with this function, because our problem, the problem that can be solved with our logistic regression is called linearly separable. And linearly separable problems means that we can solve this problem by drawing a line. So, for example, you may probably realize that that I'm slow with this, yeah, that if we do this, the problem is solved. Basically, I can perfectly separate the classes, happy ending. Now, there's a problem because there's also this stuff. And no matter what kind of like line you draw here, nothing can really separate all the blue and orange points. And of course, this is a toy problem because we're assuming there are only two classes. What if there are like, 200 classes? It's even more complicated, right? So how can we solve these problems? Let's see if someone wants to raise your hand and propose. Someone that doesn't know the answer in advance because we're trying to build up to some intuition. No? Okay, I know. Yeah?
Can we project the points to a higher dimension?
We can project the point for a higher dimension, but what do you mean by projecting?
We increase the dimension, maybe find a plane that can separate the planes.
Yeah, that depends how we move right from one representation to the other. So that's a hint. I'm going to also give you some ideas that may or may not work just to build up the intuition. So we could argue they can just stack more of this function and somehow this will solve the problem. May or may not work. We'll see now. Someone will actually say, yeah, but Simone, okay, this is a linear function, but at the end I have a sigmoid. The sigmoid is a curve, so it's not is a non-linear function. So in theory, by intuition, if this tells me, okay, it's non-linear, I could solve a non-linear problem, right? Or proposal 2, some kind of weird combination of 1 and 2, right? Whatever. But before seeing when this works and when this doesn't work, we need to learn a bit what a neural network is in general, okay? Because this is going to help you just give for granted a lot of stuff later. So first of all, at the basics of a neural network, we have the neurons. So you define a neuron by a computational unit of your network. Each network takes the linear combination, in this case, summatory, the sum of xi wij plus b, and applies this activation function. It could be the sigmoid, it could be something else, okay? And in this case, we're gonna call W weights and B biases. So the weights are learnable parameters. We saw before, like when we trained that toy neural network with just one weight, you change the value, and like magic, when you recalculate the loss, it's smaller. So we got closer to our ideal solution. So weights basically change how strongly one neuron influences the other, and we'll see soon why. We're going to define Wij as the weight from neuron I to neuron J. We have the biases, again, a learnable parameter. And, if you think about the equation of a line, for example, you may include that, if you sum a term, you kind of shifting the line a bit. So it shifts the neuron's response. So just to give you an introduction. Then we have the layers, and with the layers, we need to understand what we mean by each single thing. We have the input layer, which typically does no computation. The only thing it does, it takes an input and passes it to the network, okay? We have the output layer, which is the one that computes the final response. So in our logistic regression, this could be, the final part of the network that applies the sigmoid and outputs the probability, or the softmax layer, if we were, talking about the categorical setup. And then we have these hidden layers, and that's where things start to get interesting, because an hidden layer is an intermediate processing layer. So basically it takes whatever comes from a previous layer, applies some kind of transformation, basically the same that we saw here, and pushes forwards. So now it means that we can stack multiple hidden layers, and we can build a deep neural network. So a deep neural network is typically a network that starts having 2, 3, whatever hidden layers. Since a neural network captures patterns in the data, the more hidden layer you stack, the more your pattern becomes complicated, like refined, less of a line, for example. Important thing, you may have a neural network when you implement it that is fully or not fully connected. If it's fully connected, basically means that every neuron at the predefined layer is connected with all the neurons after and before. So we're going to see an example now, and we assume that this is a fully connected network, okay? So we have our input, a vector with, n elements. We pass it to the layer 1. There's no computation. As we say, input layer just passes it. And if we dissect, we slaughter, we open one of our neurons, the neuron was going to take the input vector, compute this HJ, this hidden result, let's say, this intermediate result, which is, as we said, do the linear combination, apply an activation function, and pass it to the next layer. Okay, we're going to have layer 2, we have layer 3. At any layer in the middle of the network, like say layer 5, what each neuron does, again, each neuron, because we are assuming fully connected, so these networks all are connected to the next ones and the previous ones, is going to take the result from each neuron of the previous layer, layer 4, really apply this combination, really apply this sigmoid function, and pass it to the next layer until eventually we have the output. So it's really stupid, isn't it? We just, combination function pass, combination function pass. But it's actually very powerful. So let's see an example of a deep neural network, and let's see how we represent its anatomy. So let's say we have an input layer. This input layer has an input vector which has 3 features, x1, x2, x3. They may be whatever, okay? So as we said, this passes the values to the next layer. So now let's say we have a hidden layer with 4 neurons. Now, let's assume a fully connected network. So each of these neurons will be connected with all of the next and previous layers neurons. So for example, if you take x1, this is going to be connected to each one of the 4 neurons. But it's also going to be true for x2, but it's also going to be true for x3. So that means that each one of those neurons will receive both x1, x2, and x3, combine them, apply an activation function, and pass it to the next layer. Now you may ask me, why are we doing this? Why do I need 4, 10, 200 neurons, right? Well, because each neuron has its own weights, which are implemented, initialized in a different way. So this one might have 0 point something, the second one might have 3.5. So when we train them, we start from different random configuration and we converge to different learned objectives, right? So it's not like they are one copy paste of the other. Otherwise, we will just be doing the same thing over and over. So yeah, as we said, each neuron computes this IntelJ at the layer 1 result. Let's say we have another hidden layer, and it goes all over and over. So each one of these 4 neurons will be connected to each neuron of the next layer, okay? So we're gonna take this and have another hidden result. And at the end, we could have 350, 200 in the layer. Let's say we just go to the output layer, okay? So again, it's fully connected. So we're gonna have full connection from each neuron of the previous layer to each neuron of the next layer. And we're gonna compute the same thing. Just this time, we're calling it Y because this is the output layer. So by definition is the output prediction. This is also a bit, again, sloppy notation. You may argue that this is a Y hat because, you know, Y is actually the golden label that arises from the data set. It doesn't matter, guys. In this context, I guess it's clear that it's the prediction. Now, let's count how many layers, neurons, weights, biases this network is. What's important that we're not going to consider the input neurons, because in here I'm considering, as I defined, a neuron as a computational unit. Now, I don't care if you consider an input layer as creating neurons, but say it, because if in the exam I ask you how many neurons does this network have, and you give me just a number, I'm gonna have to make assumptions for you. So just spend a minute to say, oh, to me, input neurons are not neurons because they don't compute. Then it's cool. Of course, don't go and say, yeah, these 3 layers don't count for me, so I'm ignoring it. That doesn't work, right? So just to be honest. So overall, how many input layers do we have? 1, yes. How many hidden layers do we have? Yes. How many output layers do we have? That's good. Okay. How many neurons do we have? I heard of 35. You have 11. If you want to count them, we are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? Because we're not considering this. If you wanted to consider this as well, 12, 13, 14, but that's not the case. How many weights do we have? Yeah, not gonna make you count, but basically we have 45 because you have one weight is one line basically. So you see that we have 3 times 4 from input to hidden layer. 3 times 4 is 12. Then we have 4 times 4, so 12 plus 16, and then you go, and if you count, these are 40 in total. Okay, cool. How many biases? Well, basically every neuron has one bias term. It's not like you do plus B1, plus B2, plus, so basically we have 11 biases, 1 per neuron, okay? So hopefully this clarifies a bit how this network works, how many of each thing we have. And now we can start seeing which one of our previous proposals work, okay? So first of all, linear problem, logistic regression. We have this this is actually literally a logistic regression because we have no hidden layer, we just have 2 inputs and an output layer. This is basically an output layer. Now, can we solve this problem? Do you expect the network to actually solve this problem? Yeah. So we play it, and yeah, fair enough. Less than 100 iteration. We solve this with like loss 0.002, so it's almost perfect. So we solved the problem very easily. This is wrong. I don't know why this is 30. Is of course is supposed to be 80. Yeah, just one of the 3,000 typos I have. Very efficiently, as we said, only 2 weights, 1 bias, 1 neuron. we could decide to make our network complex. We can add layers, we can add neurons, but it doesn't really matter because we're already perfect. Like nothing will change. You won't really get much better than this, right? At some point you hit the bottleneck of, I don't know, reality. You cannot just converge in one iteration, right? So almost never you can just say, okay, I'm just gonna add more layers and neurons. That's gonna solve the problem. Now, what about now? Nonlinear problem and logistic regression. Are we gonna solve it? Yes, no, maybe yes if we wait enough. So raise your hand if you think we're gonna solve this problem. Okay, that's very clear. Okay, so yeah, you can wait as much as you want, but basically, as we said, our model can only draw lines. There's no line that can solve this problem. So we fail. So we said we wanted this proposal. Let's stack more linear function on top of each other. Okay, so raise your hand if you think that by stacking multiple layers, we're gonna solve this problem. Okay, people think so. Let's see. The problem is if we stack. Is it playing? No, it's playing. If we stack linear functions, we just obtain another linear function. If you take the equation of a line, that's your output, and then you sum it to another term. You're just moving and shifting the line. You cannot really break out of that. So it doesn't matter how much I expand my network. We're never gonna get there. Okay. Clarification. This is kind of an extension of logistic regression, but not really, because if you look up, it says linear. So if you actually want to extend the logistic regression, we basically will have to apply linear, and sigmoid at the end. This doesn't let me do that. So basically, TensorFlow doesn't let me separate the define per layer activation function. But it will not work anyway, because after we apply 10 layers of linear transformation, we still have a linear transformation. Then we squish the value between 0 and 1. There's still going to be a boundary, which is a line. So it doesn't change. So proposal 2, sigmoid is nonlinear. Should we be able to solve this problem? We said no, because it's only one sigmoid at the end of the network. But if we stack the sigmoids, perhaps something may happen. Yeah. So as we said, one sigmoid doesn't work. It won't bend the lines and the decision boundary. So if we stack multiple sigmoids, we are sorted, because nonlinear function now, if you have, this applies a sigmoid, then we pass two sigmoids, which are now curves. They're not lines. If we combine curves, we get cones, circles, and blah, blah. And you're going to see that in some time, it's going to converge. You're already at 3,000 iterations. Just give it a time. It's just thinking about it. See, we're bending. It's going to probably get stuck on some local minima. There it is. Our decision boundary became curved. Why was it so slow? Well, this is called the problem of the vanishing gradient. We're going to see it later on with recurrent neural networks, but basically, the sigmoid derivative, if you check plug-in value into it, can only go up to 0.25. And when you combine these values, multiplies in the backpropagation many gradients which are smaller than 1, the values shrink, because if I multiply a number by a number smaller than 1, it shrinks. And you keep shrinking, and at the end your gradient is almost 0, which means you change your weights by almost nothing, and your learning is very slow. Okay, let's try something more. We have the same network, but we increased a bit, right? We have now 3 layers per network, with 3 neurons per layer. Now, if you do this, you're gonna see that it's basically the same as before, just more neurons, and it's gonna, yeah, you see the velocity starting to, yeah, it converges. Actually, much quicker. Before it was what, 5,000 iteration, now 1/5 of that. So when you increase the neurons of the network, you increase the expressivity of the network because it can draw more complex boundary lines. It doesn't mean that the previous network couldn't do it. It just means this can do it earlier because you're making more combinations. So we just add more layers and neurons. No, still this is low. We can reach the solution much, much faster than that. But stacking nonlinear functions still allows us to bend the lines and draw something which is nonlinear. And also this is a problem. So literally you can throw almost any network and it doesn't matter how heavy or non-optimal is gonna solve it. So is there a better activation function, the sigmoid? Rhetorical question, of course there is. But before, I wanted to show you a little thing. I made this quick visualization tool for you, so you can check how this works layer by layer. So on the right, you can see a network, which is not the one we saw now, but it's equivalent, basically. It just solves a slightly different decision boundary, okay? So we solve our problem. Now, what is happening at each layer now? If I go at the beginning, that's actually not the beginning, it's just the input, doesn't do anything. Let's go to layer one. Now, if I plot basically the decision boundaries of this both, sorry, to remove this, let's complete it. So if I plot the decision boundaries of these three neurons, these are linear combinations. So they are just lines. If I switch to 3D, this is going to become a plane. So yeah, we have these three planes separated because we have three neurons. And this doesn't really solve our problems, right? It's not a curve. Well, what if I switch to after I apply the sigmoid? Okay, now we have three sigmoids. You can see that basically, like if I take this one, it's just a little stretched because of course these sigmoids pass through some weights from the linear combination, so it's not a pure sigmoid. It's stretched according to the weights. The problem is that if I now see the decision boundary, if you cut a sigmoid, it's still a line. So still, first layer here, nothing. However, what happens if I now go to the second layer, which is linear, but now it's getting three sigmoids as the input? What happens when I combine three sigmoids, three curves linearly? Well, I start to obtain curves, more complex curves. So if we go to the 3D visualization, you're going to see these are not sigmoids anymore. Doesn't matter, you cannot stretch a sigmoid to make this kind of heels, I don't know, to define them. But basically, we're going there. Now, these inputs combined create three curves. And now, what happens if I take these three curves and combine them again? Then at this point, I can also show you, because we still apply the sigmoid, it's still going to become still three curves. Now, if we move to 3D, to 2D, we can see the decision boundary is already starting to look a bit more like this, but still not quite. Now, if I combine this in the last output layer, this becomes a single curve because it's only one neuron, if you will, it's one output layer. And we can remove this, pass to the final one. Yeah, and this is what we obtain. If you switch to 3D, we can also see obtain a very nice curve that actually models the boundary of our problem. And the blue points is where our non-sigmoid anymore, our curve is gonna cast values to 0. Remember, we have the decision boundary bigger than 0.5, lower than 0.5. We just morphed this curve so much that on the 0.5 became this boundary. And if we go to to the second two-dimension, that's how we go. So what I wanted to show you with this is this basically. Okay. Basically, linear combination of inputs, which are lines plus a sigmoid, boundaries are still aligned. Then we move to linear combination of non-linear function and we get curves. And then linear combination of curves gives us more complex curves. So the more we go deep in the model, the more subtle patterns we can capture. Okay. So hopefully this gave a bit of intuition why this is happening. Okay. everyone is either too scared to ask questions or got everything perfectly. That said, there is a better activation function. This is called REL, or rectified linear unit, and this converges faster than sequence, because what REL does is defining as max between 0 and x. So basically, keep 0 if the value is lower than 0, and from 0 upwards just becomes a line. And if we're gonna see these, we're gonna see that if I associate the REL, yeah, 100 iterations. So yeah, we can do much better. Of course, our previous network did it, but in 5,000 iterations, right? And this is a tough problem. Multiply this like for very complex problems. We have like, I don't know, 1,000 inputs and I don't know, 20 then layers. You're gonna run out of compute at some point. I'm gonna fill this, and then we're gonna go through the actual language models. N-gram language model. Why do we want to build an N-gram language model? Well, why do we want to build a language model? Okay, let's see. No reason. Okay, we can just finish the lecture. What is a language model? You have an idea? Ever heard of them? Yes?
Probabilistic model of language.
Yeah, the probabilistic model of the language, but what does it mean? Let's unwrap it a bit more. What is for you a probabilistic model of the language? What does it do? Right? You want to?
Yeah, I think it's assigning some probabilities to some sentence to like seeing what is the language behind that sentence.
Yeah, kinda. Your colleague says assign some probability to sentences to see what language, what language that model is. Not quite to understand which language. I mean, it can be a byproduct, but yeah.
Started for basic and say that the model is abstraction of reality. So we have a model in mental image, abstraction of our language that we use to shape our understanding of natural language.
That's starting simple. It's like it's where okay, no, it makes sense. It makes sense. I just say, okay, I see there's a bit of confusion. So I'm gonna be very simple in this. A language model assigns a probability to a sentence, like your colleague said. So for example, what's the probability of seeing the sentence, the lazy dog barked loudly? Probably is a pretty, you don't hear it every day, but it's still a pretty human sentence. Alternative, assign probability to just a word or a sequence of words, so half of a sentence, to follow another sequence of words. So for example, what is the probability that I see barked after the lazy dog? So this is what we're gonna do today, okay? We're gonna model something like this. At the most basic level, this called an N-gram model, which is the first one we'll cover, then we'll get fancy. Yeah, it's time not for math, but for probability, because we're gonna deal a bit with them. So let's refresh probabilities a bit, okay? Don't worry, you don't need to know much of it. So, categorical random variable, for example, the first word of a sentence, we're gonna see that, we have a W1, which is like word one, and, belongs to a certain vocabulary, right? We just scan some text, count all the unique words, we tokenize somehow. Word one is the first entry of our vocabulary, okay? We're gonna call this our categorical random variable. After which, we're gonna say the probability distribution is basically, for example, the probability of the at position 1 is gonna be said like this. I think I don't have other videos today, so I can go back to ink. Yeah. So the probability that word 1 is a specific instance, which we call here lowercase word 1. So for example, the probability that W1 is bad, and we're gonna have some probability for this is random. That is not calculated or anything, so it doesn't make sense. As a shortcut, we can say P of W1, P of the, blah, blah. This is just notation. Once we consider context, so not just single words, we need to deal with joint probability, right? Because now we're going to consider like, okay, what's the probability that dog comes after that? So we're starting to combine. So as a fundamental, we have joint probability. For example, the probability of the at position 1 and cat at position 2. We're gonna use this notation or some shortcuts. For example, we're gonna use a lot of this one. But you also have conditional probability. For example, the probability of cat at position 2 given that we have that. So we're actually modeling one with respect to another. And we're gonna use this like, this kind of says given. So probability of error, probability of an error in the slides. This is word 2 equals to cat given word 1 there. One day I will recheck the slides before the lecture, I promise. But that's not, today is not the day. And then we're gonna define the dependence and independence, okay? So let's say that we have two random variables, x and y. We're gonna say they're independent if basically their probability of x and y, can be expressed as the product of the probability. So knowing x doesn't influence in any way the probability of y. So for example, the probability of a coin flip resulting in head and rolling a 6 with a dice, they're not related because from the moment I flip a head on a coin, it's not gonna increase or decrease the chance of getting a dice. Now, if you're more like, how do I say in English? More stubborn, you don't believe, which is good. It's always good to be skeptical. Let's say we write all our possibilities. So we have a coin which can only do head or tail, and that's kind of 50% probability, and then we have a dice which can give us 6 values. Now, if we plot all the possibilities, so head 1, head 2, head 3, head 4, head 5, head 6, which is the one, right? Yes. Then we have tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. This is like 6 plus 6. This is 112, which is exactly the product of the individual probability. 1/2, 1 divided by 2 times 1 divided by 6. Any doubt? I'm not going to ask you to prove this in the exam, don't worry. Okay, everyone strong on probability. Conditional dependence. Two random variables are conditional dependent given z, so a third one, if the probability of x and y given z is equal to just splitting the two individual probability and making the product. So this is a bit more complex to show, and I didn't want to, bore you with a lot of maths, but let's say that you have the fact that student studied a lot and the student got a high score. So, and then you have student is strong at this subject. So we're going to call this X, Y, and Z. If you don't know Z, so you don't know that the student is strong at that subject, you might assume that X influences the probability of Y. But from the moment you know that the student is already strong, you may, this is not written in stone, you may say that X and Y are not so related anymore because then the student was already good from the first point. And so you have this conditional independent. They are independent conditionally on the third probability, okay? Third conditional situation, okay? Okay. Okay, so now enough with probability, let's go back to our language model. So given a sequence of words, our usual W1, W2, up to how many words you want, we want to calculate the probability of the sequence, okay? We're sloppy in notation. We should have wrote probability of W1 equals W1, W2, W2. We don't care. We're not gonna do it. It's gonna be clear. So we usually factorize the joint probability into a product. So we're gonna say that the probability of W1 to n is equal of the probability of W1 given some starting symbol, because we need to mark in some way that the sentence is starting. So this is usually a starting what the hell am I doing? This is usually a starting symbol. You implement it somehow as or start of sentence or some kind of representation. Sorry. And one factorization is very useful from left to right because it follows how we read text. I mean, if you're discriminating enough, in some languages, of course, there are languages that go from right to left, but we are trying to keep it simple. And again, as usual, I suggest you to go and explore how Asian NLP works, for example, is a whole different world. The problem is that this becomes heavy very quickly, because if we assume that any word depends on all the previous one, and I have a sentence of 300 words, that probably becomes heavy to calculate, right? So what do we do? Is there a way to which we can calculate this easier? Maybe we can relax a bit and assume something else? Yeah?
Let's reduce the context window.
We reduce the context windows. APA, we just apply, yeah, a Markov assumption, which says that the probability of a word does not depend on the entire sentence, but only for a part of the previous words, okay? For example, the previous 5 words, okay? Is it good enough? Is it a huge limitation? Of course, but we are dealing with constrained resources, so we cannot model like, because at some point, if I want to predict the probability of a book, and I write to Word 50,000 given the 49,000 different ones, it's gonna be a computational suicide. So for example, let's say that you have start of the sentence, the cat sat on the, and then an unknown word 7. We define E as 6, so we're calculating this word, and context is 2. So we say only depends on the 2 previous words. Then the probability of word 6 is conditional. This is wrong because for first of all, because I use I split from 1 indexing to 0 indexing. No, this is supposed to be word 7 and word 6. This is a mess. So we'll say that word 7, 5, and 6. Gonna fix this in post-pro. So basically, we're gonna say that the probability of the word 7, which is unknown, depends only on and then. So the probability on the 2 previous words. Any question about this? Because I've now probably rewrote half of the slides, and you may be confused. So, okay, no questions for now. How do we estimate the probabilities? Well, as you got a spoiler before, right? We're just counting. So this is called maximum likelihood estimation, which is a very fancy way of saying that we're gonna count how much our sentence occurs in our corpus, for example, divided by how much the previous sentence. So if we have the cat sat, we're gonna count how many times we see the cat sat and divide by how many times we see the cat. That's our probability. It's very simple. Is there any problem with this? You see where this, can we break this? Can something go wrong? Just jump, just like, is it, yeah? Yeah, if this is 0, it's a problem because we don't want to divide by 0. And even if we could, we cannot. So we do alpha smoothing. So we have this variable between 0 and 1 that can be set up heuristically or based on some experiments. You just sum it on the numerator and the denominator, multiply by the size of the vocabulary. It's a dirty fix. Is it a cheap, simple, limited way to solve it? Yes, but we're dealing with stuff from years and years ago. It works. It gets the job done. Now, how do we train this model? No clue? Someone wants to? Yes?
We start, for example, with just one word. We then count all of the occurrences of this one word. Then we introduce the 2 words context. We run, for example,
And we count, yes. But you're counting. How do you train this model? How do you plug a loss in these? Where do you know your weights or? We don't. This model has no parameters. It's just you count and that's it. It's not even a model, right? It's just counting and returning a probability based on that. So what are the limits of this? Many. First of all, long-range dependencies, because to capture, for example, the dependency between the next word and the word 10 position in the past, we need to see all the relevant 11 gram, that's how we call a sequence of 11 words in the text before. And also, it does not generalize. It doesn't matter how many times I see black car or blue car in the text. This will never tell me anything about red car. But a good language model should infer somehow the car is some kind of concept that can be related to colors. So even if I never saw the purple car, it should tell me, yeah, this is kind of I never saw it in text, but it's kind of possible. And that's not the case for our model. So the idea is, let's build a neural network that given a k-gram, so a sequence of k words, produces a probability distribution over our vocabulary. And this is called a neural language model. We're gonna see it after the quiz. So neural language models. So we said this model is very limited. Let's make it a bit better. So do you remember last lecture that we saw an embedding matrix? Raise your hand if you remember. Okay. So you want to tell us what you remember? What was it? It's okay. No, it's not graded. You can just.
So it's basically that we take so we have this embedding metrics and columns by the different languages we have, and as well as the values for the words in each language.
Yeah, so they somehow learned something useful about language, right? It was very focused on our language modeling task, right? Yeah, that's what an embedding matrix does. This time is simpler because our input is categorical features, for example, the tokens from our vocabulary, and we associate them to a representation, for example, a dense vector. And again, if you associate each vector to so each word to a vector, you might as well build a big matrix, as we saw. If you don't remember why, this is just easier than doing, n linear vectors multiplications. Go back to the lecture, we have an example on that. These vectors are now parameters of our model and are trained jointly with the rest of the other parameters. So first of all, how do we actually obtain this dense vector? Like, if I have the word cat, I need to get out the vector from it, which is learned during training, but initially it's just random. It doesn't make sense. This is done with a lookup. So basically, you just map the feature to a vector with d dimensions. This is called an embedding layer, but basically just does a lookup. You have a matrix which has as many rows as how many words you have in your vocabulary, and d is a parameter. You may say that your vectors are like 3-dimensional, so they're empty space. They may also be 300-dimensional, okay? You choose. Based on what you choose, well, in theory, if you use more dimension, you learn more. You can get something more abstract. In fact, I can tell you that word embeddings usually always have hundreds of dimensions at least. Yeah, so each row corresponds to a token, and then we execute the lookup operation via indexing. So, for example, the vector of the word W, which is word number 48, is just the row 48 of the matrix. If your symbolic feature is one-hot vector, as we saw in the previous lecture, this is just a matrix multiplication. When you multiply a one-hot vector for a matrix, you select a row, basically. So let's do a bit of a better definition. What we want is a neural network that gets a k-gram, again, sequence of keywords, and gives us an output probability over the vocabulary for the next one. So my cat is, and we want to predict cute, something like that. Each token is associated with an embedding vector. We just saw that. And the input vector is obtained by concatenating word embeddings, which means if I have my cat is, I'm going to just concatenate the vector of my, the vector of cat, and the vector of is. Can we do something else? Can we sum that? Can we average that? Can we do something? Yes, but normally we sum them. I want to make it until the end of this lecture. So X becomes the concrete function, okay? How we implement it? Your typical multi-layer perceptron with one or more hidden layer. Crucially, this is going to have some nonlinearity because I guess we can all agree that probably when we want to predict the probability of a text, there's not only two classes, right? The text is much more complex, so we want to probably draw some nice, smooth, curved decision boundaries. So let's see an example. Let's assume that the dimension of our embeddings is 50 words. Sorry, 50 dimensions. So every vector has 50 elements. And let's say that each token is a one-hot that belongs to this vocabulary times 50 if you consider the embedding matrix. Each output is a row of 50 elements, and the concatenation is 50 times 3, 150. So this is what you obtain. So we have that left out. These are one out. We're gonna look at for our matrix what is the dense vector. So this there is gonna be like I don't know 0, 1, then 0 until the position 50. And the embedding matrix is going to have a dense representation. So instead of like all 0 and 1, it's going to have 0.5, 20 plus 0.2, minus 16, completely random. And then we backpropagate and try to learn actual good values for this, right? Is a parameter now. So one-hot vector, the embedding matrix, the word embeddings that we obtain from the matrix, that again we want to learn. The nonlinearity, because the problem is complex, and now complex problems require complex networks or something, and then we map to probabilities. Up to now, is it okay? Do you see how we expand from the category log linear model? Okay. So we need to train. Now we can train this. You have these matrices, biases, and even the matrix. Where do we get training examples? How do we get the probability of the text? One has an idea. Again, don't be afraid to try. Nothing bad happens if you're wrong. Yeah?
Internet.
The internet. Yeah, that's the answer for everything. So our training example adjusts a sequence of keywords from any corpus you can find. Go on Wikipedia, go on wherever you want, on Facebook, not on 4chan probably, but use the first k minus 1 words as a feature, and then your label is the final word. And usually you train this by cross-entropy loss. This is so cool because you don't even need annotation. The annotation is inherent in the language. If I have a page where there is like, I don't know, Simone is an horrible teacher, that already exists, is in the world. I can just say Simone is an horrible and teacher is the label. I don't need to do anything. So what's the good, what's the bad of this model? Well, it's kind of heavy, basically, because it increases in parameters, the more your vocabulary expands. And if you want a realistic language model, your vocabulary is going to be very, very, very big. Also, we have to calculate a softmax at the end. When you have a vocabulary of like millions of words, calculating the softmax is very, very expensive, right? So there are some solutions, like before we're gonna cover what we did before. There's one hierarchical softmax, noise contrasted estimation. We don't care, that's not the focus. It worked for them, but now we're more in the future. We see something else. We're gonna see how we fix this, but first I'm gonna ask you, if we train that model, can we use it instead of predicting probability just to generate text? Yeah?
Yes. We could just make a it's called just a loop pretty much. A feedback loop, yes.
What do you mean by a feedback loop? Like how would it work?
We just have the output back to the inputs.
Yeah, exactly. We plug the output back to the input. So you predict the probability over the symbol S, and maybe you predict I. Yeah, you select the most probable word because again we have the distribution probability. Pick the highest value in the softmax, that's I. Predict the probability of S followed by I, and you're gonna get a probability. Maybe you'll get love. And you keep doing this, I love you so much until you predict, either a stopping criterion you define, or you have this end of sentence symbol, which is the opposite of the start of sentence symbol, right? Is it clear? Anyone? This is the moment. If it's not clear, raise your hand. Remember, yes?
How would you prevent that it doesn't keep on going in between?
You cannot prevent this goes. So your colleague asked, how do you prevent that it doesn't go infinitely? You cannot. you hope that you produce the end of sentence token, or you impose that after 20 words you stop, an early stop. But that also means that you cannot prevent it from create truncated sentences, because there's never how do you say, a length of a sentence which is safe to assume in any possible context. Any other thing? Yes?
After like guessing a word, increase the probability of other words. Like for example, if like we go along in the sentence, increase the probability of the end of sentence hopefully, and it will come up.
Yes, yeah, your colleague, that's a very good point. Your colleague said we could implement in our algorithm, the longer we go, the more we artificially inflate the end of sentence probability. So at some point we force the model. Yeah, that's also good. Anything else? Any other doubt? Yes?
Is the stopping and behavior that is very powerful when you learn a lot of the internet, or is it only for required training?
Even today, the stopping criterion is used. Like, because there are so many, so your colleague asked, is the stopping criterion something that after you learn good word embedding is necessary? What if you train on the whole internet and you don't really need, because the model kind of always generates when to stop. That's your kind of point, no?
Like when I look at an interactive language models today, so that they stop in coherent ways to stop. Is that something they learn already from the raw data, or they learn with further training?
So the question is like in the new model, the interactive ones like ChatGPT, they always kind of stop at the good point. Do they learn it from the data, or is it enforced? The answer is I don't know, because I'm not OpenAI. I would assume it's learned, because they're at this point they really train on so much text. When we use it in research, we have to stop. Anyway, most often you always want to do a max K, also because otherwise it keeps going. Especially reasoning model, like if you fire up DeepSeek with the reasoning model and you ask him what's 2 + 2, it's gonna tell 30,000 words of like the user asked me 2 + 2, so I should blah 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 in like 5 minutes, and then the answer is wrong. So let's talk about another thing. We can sample, so we can generate this sentence in many ways. The most basic one we just said, greedy. Choose always the most probable token. We can also draw randomly based on the probability distribution. So, you can, for example, start the top K different things that pick up randomly. Or you can do beam search, which is that each step of generation is generate K candidates, and it's kind of a tree structure. And then you have some policies on how to choose the most promising path. And this usually gives you less boring text, let's say. So, as we saw before, we can initialize the metrics randomly, and then after we learn, we have good word embeddings. We can also use pre-trained word embeddings. So let's say someone else trained a matrix before, and we just use this what is called self-supervised learning, because there's no really data annotation. Like the annotation is inherent in the text, as we said. We learn these new embeddings by just doing next or projection, and then we put them in our task. And in theory, you can further supervise them even more. For example, I take a matrix trained on Wikipedia, and in theory it tells me the probability of words. And then I plug it into my model and use that for sentiment analysis. I can either freeze the embeddings so they stay like that, or keep them further fine-tuning. And maybe now I can use the probability learned from Wikipedia, which is good, plus further specializing it over the task of sentiment analysis. So, you really pick your recipe for this. Good word embeddings should assign similar vectors to similar words. How can we evaluate it? Okay, let's say you have your model. How do you evaluate it? And yeah?
Simple terms, you just try to see if you have predicted the next word correctly, right? Because you can just plug in 5 words and see the 6th word is the word that's actually coming in the corpus.
Yeah, in an ideal world, that's exactly what you do. You deploy it, collect a big corpus, or ask people to, try it and say how it is. Does it produce sentences you would have thought about? Compare the distribution of the sentences with the probability of the models. But it's super expensive and time consuming, because if we define how much data do you need to to evaluate a natural language model. It is never enough, right? And you know, like let's make a quick math. The minimum wage in Germany is like about 14 euros, I think. So let's say you have a significant sample, assuming some statistical testing, if you're really, really good, 500 people, that's 7,000 euros for each sentence, for each hour of work. Then if you assume that to evaluate a sentence, it takes, I don't know, 10 seconds, and every person evaluates 5,000 sentences or 10,000, gets expensive very quickly, right? So we can also use something else, which is called perplexity. Raise your hand if you heard of perplexity. Okay, raise your hand if you're not didn't hear of perplexity. The distribution doesn't match. So there's a third component of people that okay. So consider the consent entropy. Okay, we saw it before. And let's say a corpus which has n sentences which all appear 1 divided by n times. Okay, so very simple case. Then this is the formula of the log. You remember we have this label and the prediction of our model. In our case, the label is 1 divided by n, and the prediction is the probability of our model. We can move the division out of the sum because it does not depend on I, and we obtain this very cool term. Now, if you use this as the exponentiation factor, or whatever you call it, of 2, you get the perplexity. So it's 2 elevated to the cross entropy of your model. How is it interpreted? Well, this is interpreted as how surprised your model is to see a certain text. So if you minimize perplexity, you maximize the probability. So for example, you have a test corpus of only 2 sentences, the most useless test corpus, but you still have it. Your model says that sentence 1 is 0.5, so very probable, and sentence 2 is 0.05. You calculate your cross entropy, you obtain, you know, 1 divided by 2, blah, 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 of, which is roughly 2.66. 2 elevated to 2.66 is roughly 6.3, something like that, which can be interpreted as, like your model, on average, across these 2 sentences, is as surprised as it will be if he has assigned probability 1 divided by 6, so 0.66 to each sentence. Another interpretation equivalent, the model will averagely assign 16 probability to a sentence from the test set. Another probability is like your model, whenever it's predicting the next word or like, you know, assigning the probability, is confused among 6 equally likely options. Is this good? Is this bad? I don't really know, because in theory you cannot get perplexity like 1, because then the model will probably overfit and just, you know, learn the test set. But also the test set is not trained on, so you will never get perplexity of 1. So perplexity is one of those metrics that you don't really know how to maximize. You know that in theory lower is somehow better, but there's not a minimum and maximum value, right? So we just take it as an empirical measure. Then you test it on the actual task. And in theory, yeah.
You were a little too quick on this. I'm not sure what's the PR in the bracket.
The probability of your model. You know, when you train the
sentence I.
Yes. Output, yeah. So PRI is the output of your model on the sentence I, so probability. Now I will say we are super eager for more, but I need to rest. So we're gonna take a little break and see learning what embedding and another title. Okay, so let's act as if we're not tired. So back to learning word embeddings. Okay, so far we can predict the probability of a word given a sentence, and we can also learn some useful word representation as a byproduct. But if I give you a large corpus of text and I tell you Germany is to Berlin like France is to, yeah, or man is to king like woman is to, yes. Can our model solve it? No, not really. Now, rightfully so, you could ask me, why should I care? Okay, but basically because if you find a way to do it, then we have a very nice measure of word similarity, right? Because if a model can solve this, he understands how similar the word is. You remember what was the biggest weakness of using a one-hot vector to represent words? Yeah? Yeah, it's orthonormal. So basically, every word is distant the same amount from each one. It doesn't make sense. It's just useful because it turns word into number, but it stops being useful on that. Well, it turns out there's a way to do this. So we need to talk about the dot product. So if I have two vectors, u and v, each one has n dimensions, the same number of dimensions, then I can define the dot product like this. So sum factorial of the components, or geometrically you multiply by the cosine of the angle. If I then don't care about the magnitude, so I consider unit vector, the dot product can just be simplified like this. It's just the cosine. Now, this is useful because the dot product tells you also how similar vectors are. So if I have examples like these, the cosine, this nice little root function that goes from 1 to -1, and if you check, when is the cosine at its highest point? It's in 0 and 360 angle. But that's exactly when you have either 0 angle, so the two vectors collide, or you have a 360, so again, they collide. When is the dot product the lowest, so -1? It is when you have 180 degrees. So for example, you see that if I get these two vectors, so we have 1 and 2, we get a certain amount of cosine similarity. If I now take W, which is a bit further, in terms of angle, we get 0. And in fact, if you check here, the dot product is 0 when the two vectors are orthogonal, either 90 degrees or 270. If I now get Z, which is completely opposite to U, I get -1. So with the dot product, we can represent how similar vectors are. And maybe you may now see the point that if our words are vectors, the angle can be useful to see how similar they are. Now we're going to see how we get to this. First, distributional hypothesis. Words are similar if they appear in similar contexts, right? Which is kind of similar to the other very famous statement which said you shall know a word by the company it keeps, right? So, for example, let's say you see a sentence with an unknown word like the Wampanoag, and you see Marco saw a very little Wampanoag crouching behind the tree. What's a Wampanoag without ever knowing or seeing the words? You know too much. I wanna see all the hands raised. Ah, of course, and then one next okay, yeah. Yeah, probably an animal. How do you know?
Crouching behind.
So
In exhale.
yeah, so from the context, you're understanding that, if I said Marco saw a very little monkey crouching behind the tree, it's similar, so I assume it's something similar to monkey, right? So we infer the meaning of the word based on the context in which it occurs. This is not new. There's a long line of research doing this. Basically, use what we call word context matrices. Basically, each row of the matrix is a word, and each column is a context in which the word can occur. And basically, when you go across one element of the matrix, you get the strength of the association. Now, there's a lot of stuff on that. The context is usually a neighborhood word or an entire engram, and it's typically count-based. You just, again, as before, check your corpus, how many times a word occurs in every context, and blah, blah, blah. But it's sparse, so if you don't observe enough data, some parts of our matrix will be meaningless or underdefined, let's say, underpowered. And the word vectors has a very high dimensionality depending on how you define your context. So we're going to deal with something a bit smarter than this. We're not going to count and divide or something like that. But now, we saw something similar before. You remember this from before? Okay. Now, do we agree that the columns of E learn word representation? We say that. But you may argue that also these matrix No, these are gonna. It's wrong here. It's correct in the next slide. How do I even do this? W2 also learns something similar, and we're gonna see why. Now I'm gonna do something very boring, which is plot the dimensionality of each single element of this network. Okay, so assume that we have 200,000 words of the vocabulary. That's a very small vocabulary. We don't care. And we're going to say that the dimension of our dense vectors, the dimension of the vector is 50, and J, which is some hidden dimension of the matrix, for example, is 100. Keep in mind that the size of the vectors and also the columns of the matrix these are hyperparameters. They are set up before when you implement your neural network. They don't change during the, yes?
What's G then?
Yeah?
What's G between?
Some linear, non-linearity, we said before, is a non-linear function. So basically you can change I forgot to repeat. So for the people listening to the recording in the future, the colleagues ask, what is G? G is a non-linearity. So as I was saying, these are hyperparameters. So you define before and they don't change, okay? They're the same as defining how many neurons per layer or how many layers we have, right? These are hyperparameters. If you remember back in the first lecture, we said the validation set used to decide the hyperparameters. So then you actually go back, reinstantiate your network. So the black dog, these are one-hot vectors, as we said. So what's their dimensionality? Raise your hand if you think you know. Yes?
Multiply 200K.
Yes, they have one row, because it's a vector, and they have one column for each element of the vocabulary. So 1 times 200K. What about the embedding matrix E? 1, yeah?
Multiply 50.
Sorry?
1 multiplied 50.
If it was 1 multiplied 50, it would be an embedding vector, not a matrix. Yeah? 3 by 50. These are all.
200K multiplied 50.
200K multiplied by 50, because we have one row for each word of the vocabulary. These are just 3 random words we're using, right? Which are in the vocabulary. And these are word representations. Then how about the dense vector? What's their size? Yeah?
1 by 50.
1 by 50, because we defined the dimension. What about the concatenation? This should be easy. What's the size of the concatenation of these 3 vectors? Yeah? 1 by 150. We just stack them next to each other. 50, 100, 150. What's the size of the matrix and bias? This is going to be 150 times 100. Why? Because the matrix multiplication, the vector matrix multiplication imposes that the column of the first one must be equal to the row of the second one. And as for the size, we defined it before, is our hyperparameters. We said our column, our matrix will have 100 columns, and then the row comes naturally, because otherwise we could not multiply it. And the bias vector is going to be 1 times 100, because otherwise, again, vector matrix multiplication gets the row of the first one and the columns of the second one. So it must be 1 times 100. G is also going to be 1 times 100, because it takes the input. And now you see why W2 learns more representation, because it's literally a different representation of the vocabulary. It has like 100 rows and 1 column for each entry of the vocabulary. It's just transposed. We're gonna have 1 times 200K for B2. The softmax is a vector, so again we follow the matrix multiplication and blah blah blah. So this is a bit of a more compact view. Yeah, now you should see why. That said, we typically don't get W2. You don't use it as an embedding matrix. It's just a byproduct. It was cool to see that it's not only there. And after this, I might be put this a bit too soon, but it makes sense with the topic. We're actually going to go to the second quiz. Oh, okay. Let's see how we can move from neural language models to training word embeddings, okay? So far, our model was basically trained to predict probability over a vocabulary for the next word. And we condition on the previous context. As a side product, we learn also useful word embeddings. What if I just don't care about softmax? I don't care about predicting our probability. I just want the word embeddings. So I can remove all the part after. As soon as the matrix is good, capture some meaningful web vectors, I'm happy. We can obtain a very powerful model by doing this, which is called word2vec. It's by Google, and it's now very old, not so powerful anymore, but at the time it was like Skynet is here, like it's crazy. AI will take over the world. So we do this by applying two simplification. The first one, let's teach the Markov property, not by reintroducing the full context. That's still too much, too computationally heavy, but by saying that the word does not depend only on the previous context, but only all the surrounded words. So now, if I say the K is 3 or 4, it involves both the previous and the next words. So now, basically, what I'm doing is looking into the future. So, for example, if I have the black dog, I can predict the black given the and dog. So this is the middle word. And that's the first thing we're doing. The second one, no probability distribution. We completely remove softmax. We just want to predict some score between the word and the context to tell us how similar they are. So what could such score be? Well, we wanted to prefer words in the truer context and penalize words in their true context, because this score to tell us that the black dog is good if we predict black, but the potato dog is probably bad because potato is not a word that fits in there. So does it remind you of something? This concept of preferring words in their context? Something we covered before? Well, basically, it tells us how compatible a word is with a context. So we're getting closer to the similarity we were talking about before. So the king, queen, and whatever. We do this with something introduced in the paper word2vec, which is called negative sampling. So we create an artificial task by randomly replacing a word in a context with another one. This is also self-supervised training. We don't need to annotate anything. And the task is defined like this. The output is 1 if W, C, 1 to K is a positive example, and 0 otherwise. What is a positive and negative example? Well, we take context for a concourse, like, I don't know, deep learning for NLP school. We swap the target word. So let's say we replace deep learning for NLP with something else, the potato is cool. And we train the model on assigning higher score for the actual word that was supposed to be in the context and lower for the one we replace. So we can just artificially create as many negative examples, because I can just take a sentence, choose a target word, and swap it with all the other words of the vocabulary if I want, So how do we choose the fake target words? Well, the option A is that you just filter by corpus frequencies. You just take a very, very improbable words by computing, the probability of the sentence before divided by the context. Or you can do a reweighting function, which is basically this alpha, similar to alpha smoothing, but not really. Word2vec is 0.75. We don't really care about this. It's just another option. So, okay, we have negatives. Yes?
Isn't this an next problem where we first need a word generator that is decently good at generating next words to then swap that later on? It seems like an issue. First come up with this word generator.
No, you say that you said that to do this, we first need a word generator. Wow. Why? Why cannot I go and scrap, corpuses from Wikipedia like before? Those occur. Those are natural context. Then I take a word, I swap it with another one, and that's my negative example.
The words creating the second bullet hence my conclusion, but we cleared it up, we just take the.
No, but you, as I say, we take the context and we just swap with another one. So there's not a model which swap it. So word2vec, let's talk about implementation of this, okay? So there are two variants, continuous bag of words and skipgram. I'm gonna see them both, but for now, let's do Symbol. First of all, we remove completely the hidden layer. So it's kind of a log linear model. The context is modeled as the sum, not as the concatenation of the vectors. So we just sum them. And the softmax is replaced by a sigmoid, which makes sense because we're not predicting probability. We're just predicting a score between 0 and 1. So much cheaper. So we have our context like the and dog. It's our context. We want to predict like. We have our embedding matrix that gives us the dense vector. We sum the context, of course, not the word because we're trying to predict it. Somehow we combine them because, of course, we want to, calculate their similarity. And then we pass it to the sigmoid and our loss. We tell us you should obtain 0 or 1. Now, we have the context and we have the target word. What is that somehow combine? How do we do it? How do we, compare them so that then we can pass it to the sigmoid? Anyone has an idea? Keep in mind, we're trying to obtain good word embeddings. We're trying to obtain words which are similar. Yes? You use the dot product. So how word2vec does that is exactly by combining them to the dot product, because then when I backpropagate, I train the embedding matrix in a way that maximizes the dot product for a good word in its context versus a bad word. And then I'm basically just putting all the vectors together when they are in that context or further in the opposite case. So we train a network to distinguish good word context pairs from the bad ones. We create a set, let's call it D, which have the current context word pair, which is just taken from Wikipedia, and a set D bar, which is incorrect. We swap the word for a random one, which is wrong. The goal is to estimate the probability that the probability of D is 1, given the true target in the context, and it should be high for D and low for D bar, because of course, if it's from the lower side, from the wrong side, we don't want this to be 1. We want it to be 0, ideally. And we maximize the log likelihood for this. So that's it. Just you don't need to know this, don't worry. In word2vec, for each context and the target word, we send k negative pairs. So let's say if k is just a second, if k is 10, for each context, we're gonna create 10 alternative sequences when the word is wrong. Yes?
Yeah. You said that word2vec is a self-supervised training, but this one has a labeled set of correct context pairs and set of incorrect context pairs. I thought self-supervised training meant that we do not have any labels, or I'm mistaken something.
No, okay, so self-supervised means we don't have any label. The label is self-learned, basically. We don't need manual annotation. In fact, we're not manually annotating anything here. The correct label, it's automatic, it's given in the sentence. You can automatically choose any word at any position and automatically swap for any wrong word. And it implicitly creates 1 and 0, right? So we're still not doing anything. It's like 3 lines of code to do this automatically.
So they're not called like good pairs, bad pairs, just one set of pairs and another set of pairs, and it's
no, they are called good pairs and bad pairs because one I objectively created a context that does not exist, right?
What I'm saying.
The model doesn't get it as a label yet. Yes, it does. Otherwise, how would you maximize the probability? But the label is automatically obtained because it's not like there's only 2 labels. 1 when the context exists, 0 when the context does not exist. So in that way, okay, good to go. Variant skipgram. We reverse the goal. So now we treat each of the context words as an independent context, and we try to predict the context word from the target. So before we had like I don't know, I love studying. We had love, try to predict love with I studying. Now we try to predict I given love and studying given love. So we create more tasks. For comparison, in SIBO, which is the one we saw before, we have a sequence of 2n plus 1 words, and the middle one is the target. So you have one task. Now we have the opposite. So we create 2n tasks, each one pairing the target word with a different context word. And yeah, from experiment, usually SIBO is used because it's very robust. It generalizes well. So that's good. Another variant, fast text. So one may argue that by modeling the word, I'm ignoring morphology, and that one maybe is actually pretty right. So this is not ideal, especially if you have languages with some rare words. So maybe we want to capture the root, and that's exactly what fast text does. It models each word as a bag of characters, and then each engram has its own embedding. So basically, it's almost like a subword, but you just use the individual character, then you learn specific engrams. And then you sum them up. So eating will be like the sum of ate, ate, ing, and so on. It's trained exactly like word2vec, still skipgram, still negative sampling. And now we can cover the reusability. This is basically the same thing we saw before. We can plug word embeddings that are trained before as a semantic input into any neural network, which is much better than a one-hot vector because those cannot be trained and don't make any sense besides converting words to numbers. And this is called transfer learning. We retrain the models on an auxiliary task, which is not the one we're working on, and plug into a more complex model as a retrain weight. So as I said before, train word2vec on Wikipedia, so you have general semantic knowledge. Then you have a network for sentiment analysis, and you keep training them for the actual task, or you freeze them if you don't want to retrain them. Now, I want to ask you a question. Word embeddings, including word2vec, is not great for sentiment analysis. Can you guess why? Yeah? Sorry?
They're global embedding, they're not text-based for that.
It's a bit generic. I didn't really get it. Yeah.
Assuming that like if we take this example of Wikipedia, like most of Wikipedia is going to be neutral, so there's not going to be any context with sentiment. There's not going to be emotions getting into the embeddings.
Okay, that's a good point. Wikipedia is probably, as an encyclopedia, is very neutral. But no, in general, even if I fine tune after on a corpus of sentiment analysis, it's not going to work. Yes?
Like sentiment isn't really given in like sentences, so it's not really something we can get out of the text itself. Because it doesn't say if, like, for example, this sentence is like positive or negative. It's just text, not the context.
Yeah, but again, we're plugging this. Okay, so your colleague says because next word prediction is not sentiment analysis, we're not capturing. But yes, we are plugging these vectors into a network for sentiment analysis. We're training. It still doesn't work. Now, if I ask you, what's the difference between I love you and I hate you? You of course know the difference, but those words basically appear in the same exact context. So the model will learn the love and hate are used in similar contexts, so they are similar. So basically, we have this polarity issue that we have, we use very opposite. I love you, I hate you. This is great, this is terrible, right? But the context stays the same. So the model cannot discern that. The model just knows the love and hate are somehow related. They belong to the same sentence. And we're gonna see this a bit more in a bit. Also, side note, we're now in deep learning evolution of NLP. So we're now getting into the machine learning heavy one. Now, let's go back to the beginning. Can we solve this with word2vec? We can, and we're going to show you in a little demo. Word2vec, if you do the vector of Berlin minus the vector of Germany plus the vector of France, you get as one of the closest vector to that new hybrid vector, Paris. Because I'm taking Berlin, removing its German component. What happens if I remove from Berlin everything with German? It stays a city, a capital, and then I add France, and it's gonna reorient and tell me, okay, now it's a city, but I added France. and how it moves in the space is gonna be very close to Paris. Yeah, I'm gonna obtain Paris. Now, maybe I can show you actually already. So, yeah, so this is a PCA, or is it a PCA? Yeah, so PCA is a dimensional reduction because word embeddings have a lot of dimension, like 300. So of course they cannot be represented in a three-dimensional space. PCA is an algorithm that tries to do a projection to a lower dimensional space, so it transforms 300 dimension into 3. So now we can see our vector in a nice space. We don't care about what PCA is, right? It's not a course of dimensional reduction. But if I need a keyboard, it's okay. If I write here that I want a model for the word Italy, yeah, which appears in this corpus 250 times, I see that these are the most closest vectors. So clearly, this vector captures the concept of a country, because if I compute the cosine similarity with all the vectors and list the closest one, you can see you have Germany, Greece, other countries, we have Rome at some point, we have Italy, so you can see how powerful the model is in capturing the semantic. Similarly, if I don't know, went to university, for example, yeah, we have college, school, award. So if I go to here, to university, hard to, okay, here, you can see that we have, I mean, it's hard to navigate because it's very dense, but basically shows you, it's okay if you say, but Simone, that's not far, I see many more points which are further. But remember, this is a three-dimensional representation of a point in 300 dimensions. So while the cosine similarity you see here is calculated on the whole dimension, PCA can only approximate, so it makes sense that you don't see them close. So that's a bit of a taste of how word embeddings work. Limitations. So consider this approach, which is from a paper. We use word-to-vec embeddings applied to the entire corpus where someone searches something. And we select terms that are semantically related to the query. So what can possibly go wrong? Everything. Because, for example, in this old Reve website, when you looked for COVID test, the word embedding model learned that COVID and Corona are similar, which is true, but Corona is also the beer. And so as the first, before the test, it shows you bottles of beer. So it's the similarity is very entangled, very ambiguous, definitely fun. Other limitation, similarity is completely operational. And here is like to give some justice to linguistics. We assume the words are similar if they're used in similar context. It's very risky to always assume that. We saw that before. For example, antonyms, I hate you and I love you, have very similar vectors because the word love and hate occur in similar context. So yeah, the model tends to judge that similarly. Polysyry, some words have multiple meanings. For example, bank, maybe the bank of a river, or you borrow some money. The model cram everything in a single vector, and that means they will never be able to fully represent the polysyry of that concept. And biases. Models do not have human values. AI cannot be sexist, AI is not racist, but AI can incorporate biases in the text. So they capture the patterns from the data. There is a very cool paper that you can see here on the side that says basically word embeddings encode not only stereotype biases, but also other knowledge and are problematic as towards race or gender, or even simply veridical, reflecting the status quo distribution of gender with respect to the career of the first name. So there is a very famous example. Man is to doctor like woman is to. If you plot the close vector is nurse. But a woman can be a doctor. But then from text, probably the corpus has many more instances of a woman in medical context as a nurse than men being a doctor. Or similar, there was like, I think there was like many coder is to men, men is to coder, like woman is to, or something else, either something cleaning lady or something like that. But anyway, it's very, no, it's very problematic. And I actually can show you that in an example. Yeah, so for example, you can see that if you plot word, remove the component of language and add the component of sound, one of the first nearest neighbor is music. So you can consider this, okay, what is the language of sound? Music. You can say it's not super correct, but again, I'm just making a point that this model captures some semantics. I have some other example just to make this a bit clearer. Yeah, man and screen, whatever, we know the one. But if we, for example, say Brazil, and let's say we remove Germany and add Italy with one arrow maybe. Okay, so if we plot torta is a cake in Italian. We can also say, I think this refers to the pastiera napolitana, which is another sweet. But you have trattoria, you have focaccia, which is like kind of a dough, a bread thing, prosciutto, so it's cool. But now, if I tell you nurse is to woman, like man is to doctor. One could argue it should be still nurse, right? So the model is limited in this. And as usual, we shouldn't trust these models as super valid or super objective, because they do capture the data. Again, a model doesn't care what is right or wrong. If it finds a pattern, it will just exploit it. And with this, we finally conclude. You're all free to go, and I'll see you next week. And after next week's lecture, we'll also release the first homework.